So three guys stop at a hotel for the night. The sign says $30 per room. They decide to split a room. They each pay the clerk $10 and head on to their room. 10 times 3 is 30. Well, later the clerk remembers that he forgot to change the sign and that this weekend they were supposed to be starting a new special, $25 per night per room. So he had placed $30 in the cash register. He pulls $5 back out. He doesn't have the change to distribute it evenly. He decides just to give them each back $1 and put the other two in his pocket. So they each paid $10. They each got $1 back, so they each paid $9. Well, 9 times 3 is 27. And the 2 in the guy's pocket, is that 29? What's going on? Where did the other dollar go? You ponder it for now. I'll come back to it. Okay, so this week we bring our 4-week study in epistemology to a close. Later in the course, we will have a similar 4-week study on philosophy of religion. And in the first week, we will have to revisit some questions of epistemology when we look more closely at the question of faith as a properly basic belief or a sort of justified knowing. But for now, we're looking at really a cluster of perspectives and a few last problems, especially some that may relate to our own cultural atmosphere. And then after this week, we're moving on. This week, we're going to look more closely at pragmatism, questions of knowledge in relation to science. We will try to understand the difference between analytic and continental philosophy and why that matters. We will not dive deeply, but we will survey the terrain of feminist thought in general, especially an epistemological difference between two primary waves. And we will look at the complex intersection of ideologies, that is, postmodernism. Now, what is fascinating about postmodernism is that postmodernism is known for its skepticism. It rejects so many claims on truth, and yet it asserts just as many claims on truth as it rejects. Since our culture is saturated with many of the scientific, rationalistic, and empiricist presumptions of analytic thought, as well as numerous assumptions and assertions from the continental school, the worldviews within these lectures will likely resonate with you to one degree or another, because they are asserted in our culture. Since we are now moving on to modernist and postmodern thought, let me remind you that modern or modernity refers to really the Enlightenment project, circa the 1600s up through the 1900s. Pushing past the 1900s, the first part of the 20th century is referred to as the modernist period or modernism, and then pushing away from some of those presumptions in a different direction, we have postmodernism, or that which came after modernism. This is where we come on the scene. Our culture is heavily influenced by postmodernism and in many ways, to many degrees, wrestling with its claims. Now, one point of tension that we're going to see show up this week involves assumptions concerning the nature of truth. If you'll recall that the classical theory of truth is known as the correspondence theory of truth. On this view, truth refers to whatever corresponds to reality. If it does not line up with reality, then it does not matter how sincere you are in your beliefs. Your beliefs are incorrect. They are not true. This is the traditional perspective on truth. But as we will see with some of the perspectives we encounter this week, not all, as modernism progressed on into postmodernism, it became more popular to reject rather than adopt a correspondence view on truth. So let's dive in and first contrast the correspondence theory of truth with the pragmatic theory of truth. Now, pragmatism is a philosophy that stresses the relationship between thought and action by defining meaningful conceptions of knowledge in terms of the practical effects that we associate with them, and with the truth of our beliefs in terms of how successfully they guide our actions. In short, pragmatism is a whatever works philosophy. This idea seems to work with my other beliefs, and it seems to work in practice. That is, it's an applicable idea. We're not just hanging out talking about abstract concepts. This is an idea that I can actually apply easily. So it works with my other beliefs, and it works for me. I'm able to put it into practice easily. There is, however, with pragmatism, especially neo-pragmatism, the new wave, a nagging question of relativism. Many things can work for an individual or for a community. Does that make it true? Speaking ethically, would that make it right? Well, perhaps pragmatism does succumb to relativism, but at least in its origins, it had more of a scientific approach in mind. So let's look more closely at its three earliest forms. Now, in many ways, it makes sense that pragmatic philosophy was an American philosophy, because the whole American project has been based on a do the best you can with what you've got sort of approach. Whatever works, you're pioneering great landscapes. Whether you are a farmer or a cowboy or a businessman in the city, actions speak louder than ideas. Ideas are great, but it's the actions that have to work well enough to make your living. So again, it makes sense. The earliest philosopher in this American school of pragmatic philosophy, the founder, was a guy named Charles Peirce. Now, Peirce was considered by many, including William James, whom we'll talk about next, to be one of the most important philosophers of the early 20th century. He was born in the mid-1800s and died around 1914. As a philosopher and scientist, Peirce's theory of truth really originates in his theory of meaning. We can't really have a concept of an idea without at the same time having some sort of application or context for applying that idea. When we philosophize about the ultimate nature of beauty, we might begin with the beautiful things in the world and work our way back, as Plato did, to the fact that our concept of beauty seems to be grounded in an awareness of something greater than the particular situations that we find, which we describe as beautiful. However, if we just begin with the concept itself, is it really possible to get much meaning from that? Don't you have to apply it in some sense, whether bringing it back down to apply to the particulars or describe something as beautiful within our context, or if we stay within Platonic realms or theistic realms, to point to God and describe certain aspects of beauty as involving goodness or love or excellence or things like that? Can we speak of beauty or understand beauty without some form of application? Similarly, for truth to be meaningful as a concept, truth must be applicable as a concept. Now recall that he is a scientist, and science is in the business of inquiry and investigation. And science can find answers, and from those answers we can call it truth, but is it really truth? Sometimes science disproves what it used to call true and gives us a new truth. So the first case was not really truth, right? It was a belief about truth. So Peirce says that truth is when our abstract concept of something is in agreement with our continual, endless investigation. Now, up to this point, it might still sound like a correspondence theory of truth. Here's the difference. Because Peirce downplays theory and stresses instead application, what is significant for him concerning any given theory of truth is not its potential connection to higher things or transcendental truths or those concepts about which we theorize. It's not about the theoretical connection between belief and greater reality. It's about the practical connection between belief and doubt. In his own words, if by truth and falsity you mean something not definable in terms of doubt and belief in any way, then you are talking of entities whose existence you can know nothing, and which Occam's razor would clean shave off. Your problems would be greatly simplified if, instead of saying that you want to know the truth, you were simply to say that you want to attain a state of belief unassailable by doubt. So a true belief is one that cannot be overturned or defeated. In his own words, if we were to reach a stage where we could no longer improve upon a belief, there is no point in withholding the title true from it. Peirce actually believed in God, so he's not saying that there are no higher truths. Rather, he's saying that when we speak of truth, it's got to apply to our experience. What we are to concern ourselves with is not the theory, not how the truth corresponds to greater reality, but how our belief about the truth corresponds to any potential room for doubt. He says, where would such an idea, say, as that of God come from, if not from direct experience? He actually says that skepticism is doubly condemned by the fundamental principle of scientific method, and concludes in his own words, no, as to God, open your eyes and your heart, which is also a perceptive organ, and you see him. Now, if I understand Peirce correctly, he's not saying that there is no truth that corresponds to reality. Rather, he's saying we don't focus on that. We focus on truth as it corresponds to our experience. We focus on whether our ideas work with our experiences and to what extent our experiences ought to inform our beliefs. And insofar as our beliefs about truth are corresponded with our experience and what our experience testifies about truth, then to that degree, the correspondence of our belief to our experience should also correspond back to what is true concerning the ultimate nature of reality. So Peirce's concern is speaking to epistemology, to our knowledge, and not to metaphysics or metaphysical questions. Because those who came after him, influenced by his pragmatism, advanced several ideas with which he did not agree under the banner of pragmatism, he decided to change the name of his version to Pragmatism. He decided that that term was so ugly a term that nobody would want to steal it. Next came William James. While Peirce founded the pragmatic school of philosophy, James is the one who actually popularized his version of pragmatism. James is also considered the father of American psychology. He differed with Peirce on the nature of truth, holding that beliefs do not have to be unassailable or indefeasible in order to be considered true. We do not have to wait and see how they continue to stand up to ongoing inquiry and investigation. Rather, he says, ideas become true insofar as they help us to get into satisfactory relation with other parts of our experience. So as long as a belief coheres well or works well with my other beliefs, I can call it true. He writes, you can say of it then either that it is useful because it is true, or that it is true because it is useful. Both these phrases mean exactly the same thing. So James is the one who really equates truth with usefulness. Now keep in mind that James was a psychologist, so maybe it just makes sense that he seems to have been less interested in ultimate questions of truth or concepts relating to ultimate metaphysical truth, and more interested in our mental processes of having an idea about truth and then applying that idea to our experience, or experiencing certain things and from our experiences deriving certain ideas about truth. Truth does seem to have been procedural on his view. He says, truth happens to an idea. It becomes true. It is made true. So truth is the process of an experienced or pragmatic verification. If it works, if it coheres with my other ideas, then it's true. It's useful to me to believe this. Now, James's view represents kind of a middle ground on the pragmatic question of God's existence. For James, it's a question just like anything else in our experience, and if it works for you, then there you go. He writes, "Pragmatism's only test of probable truth is what works best and combines with the collectivity of experience's demands, nothing being omitted. If theological ideas should do this, if the notion of God in particular should prove to do it, how could pragmatism possibly deny God's existence? Pragmatism could see no meaning in treating as not true a notion that was pragmatically so successful. So if the idea of God, if belief in God works well with your other views and works well for you, there you go." And he applied this to his own life as well. In the words of William Lawhead from his text, The Philosophical Journey, he writes, "As a result of years of studying science and medicine, James became morbidly depressed by the thought that human beings might be nothing more than determined mechanisms doomed to live in a closed universe where nothing escapes the domination of physical laws. If determinism is true," we'll get to that issue soon, he believed, "then his life had no meaning, for all his choices would then be as inevitable and purposeless as the blind motion of atoms. On the other hand, if he was genuinely free, then the future was open and his choices made a difference both to the course of his life and to the world on which he acted. The problem was that he did not think that there could be any definitive scientific or philosophical proof of either belief. If reason could not tell him what to believe on a certain issue, James thought, it made sense to choose the belief that would maximize his life and produce the most value when put into action. For this reason, James resolved that if he was to go on living and find any sort of meaning in life at all, he would have to commit himself to the thesis that free will is not an illusion, and base his actions on that conviction." James wrote, "My first act of free will shall be to believe in free will. I will go a step further with my will, not only to act with it, but believe as well, believe in my individual reality and creative power. Life shall be built in doing and suffering and creating." Lawhead concludes, "This personal example illustrates James's version of the pragmatic method for forming our beliefs. As he said, truth is a function of what works best and combines with the collectivity of experience's demands. According to James, it is better to believe in free will because it will allow us to believe that our choices make a difference to the world, and it will make our moral struggles meaningful, whereas determinism will not. Hence, in this very personal sense, the consequences of believing in free will lead to better results." James writes, "Of two competing views of the universe, which in all other respects are equal, but of which the first denies some vital human need while the second satisfies it, the second will be favored by sane men for the simple reason that it makes the world seem more rational." So while there is overlap, we've already got a great deal of difference between these two schools of pragmatic thought. The next and most famous of the early American pragmatists was John Dewey. He tended to avoid talk of truth, but spoke rather of warranted assertability. For Dewey, truth is not really something that is fixed, but it changes as the problems we face change. So his version of pragmatic philosophy is called instrumentalism because it presses the point that our beliefs are instruments that we bring to our situations, our experiences, our problems, and a belief is true or good or works for us insofar as it is able to help practically solve the problem before us. The beliefs to which we hold, we have received through a process of inquiry, and we believe as we do because these conclusions fit best with our experiences and offer the most promise for handling future situations or resolving future problems. However, the world is always changing and we're always experiencing new situations, and this is a scientific process. Thus, inquiry can never cease and belief can never be fixed until the end of all things, at which point we will know that that which throughout all the course of our experiences continued to work for us, that is truth. Now, Dewey had his hands in many things, including philosophy of art, but he is probably most famous for his contributions to education. Applying his scientific worldview and his pragmatic philosophy, he advocated for a progressive education. He was part of the progressive education movement, which de-emphasized traditional methods of teaching or traditional standards of knowledge, certain ideas or concepts that a student ought to know, or certain things that students ought to read, stressing instead an experience-based learning, as well as an instrumental or pragmatic philosophy of education. So education is not in the business of equipping students with truth or true ideas. Rather, it's in the business of helping them to develop ideas that work for them or experiences that are useful to them. And this can show up in a number of ways. So while pragmatic philosophy is empiricist leaning, Dewey was the more staunch empiricist of the three. As we saw with Peirce's view, there is certainly room for higher truth. With James, it's a little ambiguous, but there's at least the possibility if it works for you. For Dewey, there's not really any room for any notion of higher truths or eternal values. Truth strictly amounts to that which works for us, and it's all tethered to experience. And this is why his version is called instrumentalism, because our ideas, our theories, are never really measured by whether or not they're true or false. They're always measured insofar as they are useful. How effective is this theory in explaining something? Or how effective is this idea in working for me? So, generally speaking, pragmatism holds that when we speak of truth, we are not speaking of that which corresponds to the way things actually are. When we speak of truth, all that truth can really amount to is that which is agreed upon by our critical community of investigators or inquirers once all of the evidence and information is in. So here you can really sense the empiricism. There is no reservoir of knowledge concerning truth that we have and hold. Rather, truth is a process, and as we continue to experience and investigate our world and new information comes in, we put that together, and whatever we agree upon, that we can call knowledge, or the best grasp of truth we have at the moment. And truth will ultimately refer to all the knowledge and information and evidence that came in upon which we all agreed. So it's really tethered to the critical community of inquirers. Whatever the community agrees to, that amounts to truth. It worked for them. Now the real question here is, why suppose once all the evidence is in, that whatever we call truth based on that because it works for us will actually be true? Can we not make mistakes in our reasoning? Can we not look at evidence and get things wrong? Cannot things that work for us, or that we sincerely believe, and it coheres with our other beliefs and does not cause any cognitive dissonance, cannot these things sometimes be bad ideas? So now you've met all the players, and as far as that ultimate question of epistemology goes, how do you know that you know what you think you know? Well, the pragmatists have an answer. My beliefs work. My beliefs cohere with my experiences, and my experiences cohere with or reinforce my beliefs. But what about that charge of relativism? Does pragmatism succumb to the problem of relativism? Well, not in the case of Charles Peirce. Peirce wrote, "There are real things whose characters are entirely independent of our opinions about them. Those realities affect our senses according to regular laws, and by taking advantage of the laws of perception, we can ascertain by reason how things really and truly are." That certainly does not sound relativistic. James, on the other hand, was ambiguous and seemingly inconsistent. Sometimes he seemed to lean toward an objectivist view, other times he seemed quite relativistic. So it's hard to say. Dewey, however, does advance a sort of relativism. Although he does not advance an individual-based or subjectivist view of relativism, he does embrace a cultural or contextual or situational perspective on truth and meaning. In the same way that scientific theories often become outdated and need to be updated, so too other beliefs or theories of truth are tied to sociocultural contexts insofar as they work for us, and when they no longer work for us, then we seek new truths. So for Dewey, even though there is no absolute universal fixed truth, we should embrace a pragmatic philosophy because doing so provides the most useful approach to our experience. In other words, he is convinced that a whatever works philosophy will work best. Of course, the pragmatic relativist faces a pressing question. Upon what grounds can it be said that pragmatic theory is true? When one group's pragmatic truth clashes with that of another, what then? Moreover, if there are no ultimate truths to be asserted at this point, we will not have any truth until all the facts are in, if we can know it then. To claim that truth is whatever works, and we know that this is true because it works, is this not twice problematic? First, because we have asserted pragmatism as truth, and second, because to say that it's true because it works, isn't this circular reasoning? Now, to be clear, this is not a challenge to the idea that our understanding of truth is tethered to experience. Recall that Kant said it's impossible to separate our reasoning from our experiences. Rather, this is a challenge to the assertion of pragmatic theory that truth amounts to whatever works within our pragmatic experience, and not to any assertions of corresponding truth gleaned from our pragmatic experiences. So in summary, pragmatism is a truth as coherence rather than a truth as correspondence view. The question remains as to whether a belief or beliefs can be sincere, whether beliefs can cohere with other beliefs and yet still fail to correspond to reality. For the pragmatist, as long as a belief coheres with other beliefs and is useful to believe because it makes life more meaningful, it is true. Okay, now let's turn to the question of scientific knowledge. What is the nature of scientific knowledge? Now, for some of you, science gives us truth, science gives us fact, and that's the end of it. But that is one of the questions of epistemology. To what extent can we know what we know from science? Does science actually give us truth? Now, the term scientist was not actually used until the 1800s, and it was coined by a philosopher. Until that point in history, those whom we call scientists, they just thought of themselves as philosophers. And philosophers throughout history have had a significant impact upon the developments of science. For example, the ideas of both Pythagoras and Aristotle had great impact upon the scientific revolution. Aristotle's physics, especially as it relates to his system of classification or taxonomy, became the basis of study for the physical world for roughly 2,000 years. But not all schools of thought attribute to science the same level of authority. As we pushed beyond the modern era on into modernism, Western philosophy kind of split into two broad paths. The analytic school continued to explore and develop ideas concerning rationalism and empiricism, whereas the continental school, to oversimplify, was more interested in exploring the mind and subjective experience and the relation between subjective experiences and the other questions of philosophy. Both were influenced by Kant, but they locked onto different aspects of what he said. As to the question of science, the analytic school then, understandably, more rationalist and empiricist in nature, tended to give science more authority than the continental school. In fact, there was one point in the analytic tradition where science was essentially crowned king over all knowledge. And this is what has attributed to our conceptions about facts and values, where many people assume that fact means proven by science rather than referring to the way the world actually is, even if it cannot be demonstrated empirically. Whereas the analytic school has tended to attribute greater degrees of certainty to the claims of science, many ideologies growing out of the continental school have expressed in different ways and to differing degrees some level of skepticism concerning the overall authority of science to speak of truth. In general, there are two broad camps concerning the epistemological question of science: scientific realism and scientific anti-realism. Scientific realism is the traditional view that science is capable of giving us true accounts of the world, and that the entities that play a role in our best scientific theories actually exist independent of our conceptual framework. On the anti-realist view, on the other hand, scientific theories do not give us a literally true account of the world, but they do provide us with fruitful models, calculating devices, and useful fictions, ways of thinking about things, ways to systematize our experience. So science doesn't really speak of truth or the way things actually are, but they present us with a story of sorts that helps us to make sense of things as best we can. On this view, our theories are really just attempts to grasp at a sense of order to help explain our observations or experiences. So let's ponder this for a few minutes. Have we ever really had true knowledge? Can we really say that we know we have understood the way the world is? Don't our theories keep changing as we go throughout time? What was the Copernican revolution? It was an overthrowing of tradition. So theories at any given stage in history are put forward, and they may be successful, but they are only sufficient insofar as there is no counterpoint. But at some later stage in history, when there is counterpoint, those theories are no longer useful or no longer sufficient, and so they are replaced, overthrown. So in the early 1700s, Isaac Newton advanced a particles-based theory of light. By the time we get to the 1800s, this is replaced with a wave-based theory of light. By the time we get to the 1900s, Einstein has revived and expounded upon Newton's particle-based theory, and later it was discovered that light behaves both like particles and waves, so we get a wave-particle duality theory. So let's pause here to look at a few videos in order to consider how one theory, such as Einstein's theory of relativity, can challenge prior perspectives, expand contemporary perspectives, and also cause problems for new, supplemental, or alternative theories that attempt to explain everything. When our new theories disagree with the old, is it time to reject the new or update the old? Or do we just glean what we can from each theory and move on because, as the anti-realist argues, science isn't really in the business of giving us truth anyway, it just gives us useful models for organizing and exploring further our experience.
One of Albert Einstein's most important insights is that empty space can be curved, and what we call gravity is really just a consequence of those curves. That's not an easy concept to grasp, so scientists use all kinds of analogies to help explain it. The most common is probably the grid dipping under a planet, star, or galaxy. We asked two physicists to walk us through the concept.
It's really about how light in space behaves. Up until Einstein came along, we had a way of thinking about what space was, about what mass was, that was very different. You know, usually we think of space as just being this empty thing. And we think of it as if you've got light traveling, it travels like a laser. It travels in a completely straight line.
It's only when using very precise equipment like the Hubble telescope that it becomes obvious that isn't true. We can see that if light had to pass close to something massive on its way to Earth, it arrives at a weird angle.
So light rays are not propagating already along straight lines. They are propagating along curved lines.
This is one of the major predictions of relativity, that matter curves space-time and that we can see that curvature simply by observing how light gets to Earth.
It follows what space does. So if space curves, then light is going to curve.
When you take a particle which has mass and put it to space-time, then the particle actually distorts the geometry of space-time, which becomes not flat but curved. And this is the curvature of space-time.
And that's what the bent grid, or so-called trampoline, is meant to illustrate, helping us get our heads around how space curves in the presence of matter.
And the trampoline seems to be very successful in helping people to kind of get this idea.
If you take a big sheet of rubber and put on that rubber some heavy body, it will make that rubber kind of curved.
And now you start rolling marbles across it. You can get them to go all the way across, but they'll bend as they get close to that dip in the trampoline.
This is what happens in the real world. And so this is how we can trace the presence of curvature in the experiments with the light rays.
Unfortunately, the trampoline analogy only goes so far because the universe isn't two-dimensional, but it's a good starting point.
But then you have to translate it into 3D space. When you try to conceive of that in 3 dimensions, it just messes with your head completely.
We're used to thinking of space as the emptiness in which things happen, like an empty warehouse ready to be filled, or a theater stage on which the events of the universe play out. But general relativity predicts that space is not just emptiness, it's a physical, dynamical thing, and that prediction has been borne out by many, many experiments. Space can bend because of matter and energy, curving the paths of objects that move inside of it. It can ripple with gravitational waves, and it can expand, creating more and more space in space. All of these seemingly different phenomena can be described by one idea: curvature of space, or space-time. In flat regions of space, like if there's no energy or matter nearby, objects traveling along parallel paths stay along parallel paths. In positively curved regions of space, like near planets or black holes, parallel paths converge, and in negatively curved regions of space, parallel paths, or even paths pointed at each other, diverge. But what about space as a whole? If space is positively curved everywhere, then there's only one shape space can be: a giant hyperspace potato. If you went in one direction for long enough, eventually you'd end up in the same place you started. If space is flat everywhere, its shape could be simple, just extend out straight to infinity. Or it could loop around in a periodic way, like in some video games. And if space is negatively curved everywhere, sports would be impossible. So which is it? There are basically two ways to measure the large-scale curvature of the universe. One is to measure the angles inside of triangles. If space is flat, the angles will add up to 180 degrees. But if space is curved, those angles will add up to more or less than 180 degrees, depending on the type of curvature. Cosmologists have done the equivalent of measuring our universe's triangles by looking at a picture of the early universe and studying the spatial relationship between different points on that picture. The second way to measure curvature is to measure the thing that causes space to curve in the first place: the density of energy and matter throughout the universe, which cosmologists have also measured. It turns out that in both cases, measurements show the universe to be pretty much flat, with a 0.4% margin of error. But before you get disappointed that we don't live in a cool cosmic hyper-potato, let me tell you one big problem. The fact that we live in a flat universe appears to be a gigantic, cosmic-level coincidence. If the universe had just a little bit more mass and energy, space would have curved one way, and if it had just a little bit less mass and energy, space would have curved the other way. But we seem to have just the right amount to make space perfectly flat, as far as we can tell. This perfect amount is the equivalent of 5 hydrogen atoms per cubic meter of space, on average. Those big empty parts of space make up for all the atoms we have crammed in here around us. If instead there were 6 hydrogen atoms per cubic meter of space on average, or 4, the entire universe would have been a lot more curved, or a lot less. And we so far have no idea why our universe has the mass energy density it does. When it comes to the curvature of the universe, our knowledge falls flat.
The first problem introduced by the old Big Bang Theory was called the horizon problem.
Which is basically the problem of trying to understand how the universe got to be so uniform. Why does the universe look the same over there as it does if you look that way?
And why was this a problem? Well, think of a cup of tea. If you pour milk into your tea, it'll take some time for the molecules to interact and eventually come to about the same temperature. But it won't happen instantly. The same is true on a larger scale. The fastest any two objects can interact is as soon as light has had time to travel between them. Well, according to conventional Big Bang Theory, light hasn't had time to travel from one side of the observable universe to the other. So why should they be at the same temperature?
So inflation gets around that in really a very simple way. That if we trace back the universe that we're looking at now to what it looked like before inflation, it was vastly smaller than anybody would have thought without the inflationary theory.
Vastly smaller is not an exaggeration. Before inflation, everything in our observable universe fit in a volume a billionth the size of a proton. Then the universe went through 2 expansions, inflation and after. Both expanded space by a factor of 10 to the 28, but the second expansion took 13.8 billion years. That first expansion, inflation, took 10 to the minus 38 seconds. It's just an unfathomable rate. Back to you, Goose.
And it was during the time before inflation, when the universe was incredibly tiny, that there was plenty of time for every piece of the universe to communicate with every other piece, and plenty of time for it to come to essentially a uniform density of energy and uniform temperature.
So now we know the universe was super tiny. Well, the true genius of Guth's theory was not the incredibly tiny universe, but how it could have expanded so fast. Inflation provided the mechanism for expansion, repulsive gravity.
In Newton's theory of gravity, gravity was always attractive. There just was no other option. But it turned out that this more complicated theory of general relativity actually allows for the possibility of a repulsive form of gravity.
Yes, in very specific circumstances, gravity can provide a push, not a pull. It comes from something called the false vacuum, a state of matter in the early universe that allows expansion of space while the mass density stays constant. And that understanding for the mechanism of inflation brought a solution to the horizon problem.
In the first 2 videos, we saw how the theory of general relativity was really a game changer when it comes to studying space. This encouraged new ideas, which led to other theories, such as the Big Bang Theory. As we saw in the last video, these other theories raise new problems, and so then we need new theories to deal with those problems. Perhaps the anti-realist might challenge if we keep having to tack on theories to explain the theories that explain our theories. Then to what extent can we really say that we are explaining the world as it is, rather than simply strengthening ideas about the way the world could be? So there's a spectrum of anti-realism, and to be a scientific anti-realist does not necessarily mean that you're anti-science. Rather, you always carry a degree of skepticism as to the authority that science has to speak of the way things are and assert certain ideas as true. So you could be a pragmatist and think that scientific theories are useful insofar as they work and help us develop technologies that make our life better or more meaningful. And yet you may be uncomfortable attributing to science or scientific theories the degree of certainty that others seem comfortable attributing. 2 more videos for you. Recall that we began our exploration of epistemology with the problem of perception. It's still a question. To what extent can we trust our senses? Well, science is in the business of observing and reporting what it perceives. Is this a problem? The theory of special relativity advances claims on scientific knowledge, and yet at the same time it challenges our perception. Now, prior to having our perspective challenged, science was working to make the data work. Now that we've had our perspective challenged, we do what we can to make the data work and to find new data to fit the new perspective. But the question remains, Do our current claims on scientific truth, though evolved from prior challenges, still need to be challenged? Do we have the information now to state claims of knowledge, or will we one day also have to challenge this perspective in order to move in a new direction?
Bob is on this amazing hypothetical train. Oh, and the front of the train has a headlight. From Bob's perspective, standing on the train, the light from the headlight is moving away from him at the speed of light. So the train is moving at half the speed of light, but at the same time it's shooting out light from the headlight that's moving at the speed of light. You'd think that from your perspective on the platform, it would look like the light coming from the headlight was moving at 1.5 times the speed of light, because it would have its own speed plus the speed of the train. But that's not true, because light always has to move at the same speed through a vacuum from any perspective. So from your point of view on the platform, that light wouldn't look like it's going faster than the speed of light. It would just look like it's moving at exactly the speed of light. As counterintuitive and strange as that sounds, special relativity explains why. The theory of special relativity was proposed by Albert Einstein in 1905. It explains the behavior of things that move very, very fast, as in a significant fraction of the speed of light, where regular Newtonian physics doesn't always apply. It's called special relativity because it only applies to specific situations where the different frames of reference aren't accelerating. They're called inertial reference frames. In our train example, the two reference frames are the perspective of someone standing on the train and someone standing on the platform. Neither reference frame is accelerating, so they're inertial, and so special relativity applies. Now, special relativity is built around two main assumptions or postulates. The first says that the laws of physics are all the same in all inertial reference frames. It doesn't matter whether you're on the train or on the platform, the same equations will apply. This has to be true because there's no real way to distinguish between reference frames. For all Bob knows, from his perspective on the train as it passes the platform, he's sitting perfectly still. While the platform zooms past him, or the platform could be staying put while he moves past it. The first postulate tells us it doesn't matter. The physics will play out in the same way no matter what. The second postulate says that the speed of light in a vacuum is the same for all observers, about 300 million meters per second, always, whether or not the light source is moving. So even if light is coming from a train that's moving at half the speed of light, the light itself is still moving at about 300 million meters per second. And this is where things start to get weird. You already know that speed multiplied by time equals distance, but special relativity tells us that when it comes to light, speed is always constant, which would mean that the other two variables would have to change, time and distance. And they do. When time changes, that's called time dilation. And when distance changes, that's called length contraction. Time dilation occurs when another reference frame is moving relative to you. So time in that reference frame slows down relative to the time you measure. You can see why if we go back to Bob's train. Say Bob stands on the side of his train car that's closer to the platform, and he's facing a mirror on the opposite side of the car, 5 meters away. He shines a flashlight towards this mirror, which reflects the light right back towards him. From Bob's point of view on the train, the situation's very simple. The light traveled straight to the mirror and back, a distance of 10 meters, at the speed of light. Sure, looking through the window, you saw the light travel to the mirror and back, but meanwhile, the train was still moving. While the light travelled towards the mirror moves sideways relative to your spot on the platform. And while the light travelled back toward Bob moved even further sideways. The result is that you saw the light travel diagonally, as though its path formed two sides of a triangle. From your point of view, the light travelled a greater distance than it did from Bob's point of view. But special relativity tells us that the light's speed was exactly c, even though it travelled a greater distance. And if the light travelled a greater distance at the same speed, then it must have been travelling for longer. You and Bob are both timing the exact same series of events, but you're measuring a longer time than Bob is. So from your perspective on the platform, time has slowed down for Bob. Because time can pass differently for people depending on their frame of reference, there's also no universal concept of simultaneity. In other words, something that seems simultaneous to you might not be simultaneous to Bob. Say you see a flash of lightning at each end of Bob's train at the exact same time he passes you on the platform. You see both flashes at the same time and they're both the same distance from you, travelling at the same speed. So you can conclude that lightning struck both ends of his train at the same time. But from Bob's perspective on the train, that's not what happened. Because while the light is travelling from each end of the train to his eyes, he's moving. At the moment that you see both flashes, Bob has already moved past you, so he's seen the flash from the front of the train, but only that one. Then he sees the flash from the lightning that struck the back of the train. Light always moves at the speed of light, no matter what the reference frame is. That's the rule. So to Bob, lightning must have struck the front of the train before it struck the back of the train, even though they seem simultaneous to you. Does your brain hurt yet? As if time slowing down wasn't weird enough, there's also length contraction. Length contraction means that if something is moving relative to you, its length in the direction that it's moving will seem shorter than it would if it wasn't moving. So you might have measured the train to be 100 meters long before it left the station. If Bob measures the train from where he's standing, it would be 100 meters long. But from your perspective on the platform as it moves past you, the train will be shorter. Since length contraction isn't something we see in everyday life, it isn't part of our intuitive sense of physics. So special relativity tells us that because light always travels at the same speed, time dilates and length contracts to compensate. Space and time, they're directly connected to each other. That's what people mean when they talk about four-dimensional space-time. If you're describing something physically, it's not enough to just talk about its position in three-dimensional space. You also need to take time into account.
To understand the true nature of reality, we looked at things up close and were amazed. Wondrous landscapes in the dust, zoos of bizarre creatures, complex protein robots, all of them made from structures of molecules made up of countless even smaller things, atoms. We thought they were the final layer of reality until we smashed them together really hard and discovered things that can't be divided anymore, elementary particles. But now we had a problem. They're so small that we could no longer look at them. Think about it. What is seeing? To see something, we need light, an electromagnetic wave. This wave hits the surface of the thing and gets reflected back from it into your eye. The wave carries information from the object that your brain uses to create an image. So you can't see something without somehow interacting with it. Seeing is touching, an active process, not a passive one. This is not a problem with most things. But particles are very, very, very small. So small that the electromagnetic waves we use to see are too big to touch them. Visible light just passes over them. We can try to solve this by creating electromagnetic waves with more and much smaller wavelengths. But more wavelengths means more energy. So when we touch a particle with a wave that has a lot of energy, it alters it. By looking at a particle, we change it. So we can't measure elementary particles precisely. This fact is so important that it has a name. The Heisenberg uncertainty principle, the basis of all quantum physics. So what does a particle look like then? What is its nature? We don't know. If we look really hard, we can see a blurry sphere of influence, but not the particles themselves. We just know they exist. But if that's the case, how can we do any science with them? We did what humans do and invented a new story, a mathematical fiction. The story of the point particle. We decided that we would pretend that a particle is a point in space. Any electron is a point with a certain electric charge and a certain mass, all indistinguishable from each other. This way, physicists could define them and calculate all of their interactions. This is called quantum field theory and solved a lot of problems. All of the standard model of particle physics is built on it, and it predicts lots of things very well. Some quantum properties of the electron, for example, have been tested and are accurate up to 0.0000000000002%. So while particles are not really points, by treating them as if they were, we get a pretty good picture of the universe. Not only did this idea advance science, it also led to a lot of real-world technology we use every day. But there's a huge problem: gravity. In quantum mechanics, all physical forces are carried by certain particles. But according to Einstein's general relativity, gravity is not a force like the others in the universe. If the universe is a play, particles are the actors, but gravity is the stage. To put it simply, gravity is a theory of geometry, the geometry of space-time itself, of distances which we need to describe with absolute precision. But since there is no way to precisely measure things in the quantum world, our story of gravity doesn't work with our story of quantum physics. When physicists tried to add gravity to the story by inventing a new particle, their mathematics broke down. And this is a big problem. If we could marry gravity to quantum physics and the standard model, we would have the theory of everything. So very smart people came up with a new story, They asked, what is more complex than a point, a line, or a string? String theory was born. What makes string theory so elegant is that it describes many different elementary particles as different modes of vibration of the string. Just like a violin string vibrating differently can give you a lot of different notes, a string can give you different particles. Most importantly, this includes gravity. String theory promised to unify all fundamental forces of the universe. This caused enormous excitement and hype. String theory quickly graduated to a possible theory of everything. Unfortunately, string theory comes with a lot of strings attached. Much of the maths involving a consistent string theory does not work in our universe with its 3 spatial and 1 temporal dimensions. String theory requires 10 dimensions to work out. So string theorists did calculations in model universes, and then tried to get rid of the 6 additional dimensions and describe our own universe. But so far, nobody has succeeded, and no prediction of string theory has been proven in an experiment. So string theory did not reveal the nature of our universe. One could argue that in this case, string theory really isn't useful at all. Science is all about experiments and predictions. If we can't do those, why should we bother with strings? It really is all about how we use it. Physics is based on maths. 2 plus 2 makes 4. This is true no matter how you feel about it. And the maths in string theory does work out. That's why string theory is still useful. Imagine that you want to build a cruise ship, but you only have blueprints for a small rowing boat. There are plenty of differences: the engine, the materials, the scale. But both things are fundamentally the same, things that float. So by studying the rowing boat blueprints, you might still learn something about how to build a cruise ship eventually. With string theory, we can try to answer some questions about quantum gravity that have been puzzling physicists for decades, such as how black holes work or the information paradox. String theory may point us in the right direction. When used in this spirit, string theory becomes a precious tool for theoretical physicists and help them discover new aspects of the quantum world and some beautiful mathematics. So maybe the story of string theory is not the theory of everything. But just like the story of the point particle, it may be an extremely useful story.
So the fact that any given scientific theory is always wrestling through its ideas, sometimes returning to the old, sometimes pressing forward to the new, maybe to eventually reject the new and return to the old, or look for some sort of synthesis. Whatever happens, the question arises, to what extent can we attribute truthfulness to the conclusions of a theory at any given moment in history? Well, the anti-realist believes that even though our theories are not really true, and even though they're just attempts to grasp a sense of order out of experience, they can still be useful. For example, the statement that the average American family has 2.4 children, well, that cannot be literally true. And yet it can still be useful for socioeconomic planning. Now, the scientific realists do have a number of replies, and we do not have time to look at many of them. We're just dipping our toes in the water here. But one of them would be that as we go throughout history and we change or develop our ideas, we're not really overthrowing the tradition before it. There are many things from the prior tradition on knowledge that are carried into the new theory. And so it is a misrepresentation to look at history and say, well, we all believe this way, and then suddenly we all believe a totally different way, and now we believe a new way, or now we've gone back to the old way. Well, that's not true. At any given point, there are things that we are certain of. We develop new ideas, and we piece those ideas with the old things that we were certain of, and we modify the things that don't fit anymore. Note that to advance by changing some things about a prior theory requires a realist view. You've got to believe that things really are a certain way and that you've got it wrong in order to change your theory. Well, if changing your theory advances scientific inquiry, The realist will argue that only scientific realism is able to make sense of the fact of scientific progress. Otherwise, it's just kind of dumb luck that we tweak this and we advance our technology. Unless our theories match something about the way the world is, progress doesn't really make sense. So let's dig at the terminology surrounding scientific knowledge. First of all, in case you didn't know, there is a difference between hypothesis, theory, and law. Hypotheses refer to any proposed explanations of a natural event or an observation. To label something a theory means that you are suggesting it is not just a mere guess, but it is a contention that is supported or has been supported continually over time by experimental evidence or other forms of continual corroboration. And yet the evidence or agreement concerning the evidence is not significant enough yet to warrant calling it a law. A law refers to a theory that has a great amount of evidence in its support. For example, the law of cause and effect, laws of planetary motion, the law of gravitation, the laws of thermodynamics, etc. Another question involves the nature of scientific observation. On one view, we are passive or neutral observers. We observe something, and from that we derive a theory based on the observation. Others will disagree with this and say that all data are theory-laden. So theories are not the kind of thing that we derive from observations. Rather, we bring our theories to our observations. Our theoretical frameworks concerning what we expect to see, to a significant degree, guides our interpretations of our observations. Sometimes you see what you want to see. It's harder to find that which you don't expect to see. This is why Karl Popper thought it necessary to differentiate between science and pseudoscience. Whereas true science seeks disconfirmation, pseudoscience seeks confirmation. This is why there's somewhat of a tension between Eastern and Western traditions of medicine. Whereas Western medicine tends to be science-driven, traditional holistic forms of Eastern medicine are more of a pseudoscience. In the West, we treat the issue. In the Eastern traditional holistic approaches, you try certain practices to prevent. From one perspective, you give shots if you get sick. From another perspective, you eat certain things and practice certain habits in order to prevent becoming sick. It's easier to confirm that shots prevent certain things or that certain medicine made you feel better than it is to confirm that eating certain things is what kept you from getting sick, or that the acupuncture releasing your blocked qi is what stimulated your body to heal itself. According to certain Eastern traditions that have worked their way into our Western massage culture, certain practices like healing touch or Reiki are able to heal the body or help the body. And this is an energetic touch, heat or energy coming from the hands or palm of one person and affecting the body of another, or removing the negative energy from their aura and replacing it with a positive therapeutic energy. This is pseudoscience. Now, when I place my hands on you, you're going to feel a heat, or when I place my hands over you, you might feel a tingling. That's just the Reiki or the healing touch. Do you feel that? Oh yeah, I think I do. Wow. You see the problem. There's not really any way for practitioner or recipient of the therapy to prove that they experience what they say they experienced. It has no room for disconfirmation, so there's a confirmation bias involved. And sometimes, especially if you're desperate for something, you might be more likely to see things where they are not. Now, to be clear, at the moment, I am not speaking to whether or not people can experience such things. Rather, I am just pointing out that these kinds of claims are not falsifiable. They have no room for disconfirmation, and so they are quite problematic when asserted as truth or a claim on knowledge. Scientific claims must include 4 criteria. As Occam's razor says, the simplest explanation is most likely to be true. A scientific claim must also be able to explain a wide range of phenomena. Good scientific theories will not simply organize facts, but should also be able to reach out and predict new phenomena. And most importantly, a claim must be falsifiable. Falsifiability refers to the criterion that it must be theoretically possible to disprove a scientific claim in order for that claim to count as a scientific claim. And the last epistemic problem I want to leave you with today comes from Thomas Kuhn, who argued that scientific truth is just revolutionary shifting according to really a power play over knowledge. Just like political revolutions are new ideas arising to overthrow the old ones, and you have staunch traditionalists holding to the old ways and progressivists stressing the new ways, and really truth for that generation amounts to whatever wins out. The view or the perspective that wins that culture war over knowledge. So on this view, Thomas Kuhn is saying that truth, here we're talking about scientific truth, just amounts to a shifting according to whatever is voted as most popular. That means that all truth really amounts to is a shifting web of beliefs, far from actually corresponding to a way things actually are. On this view, scientific knowledge just amounts to perspective wars and power plays. In the words of James Fieser, on this view, science is not cumulative. Our present theories are not built upon some secure foundation of past theories. Instead, scientific knowledge shifts according to our current paradigms, and once again, the issue of relativism arises. These paradigms are webs of belief that are held by the scientific community at the time. Truths in science, then, are relative to these shifting webs of beliefs. So on this view, science itself is relativistic. So ponder that for now, and next time we will pick up with a brief primer on feminist epistemology as well as an overview of several postmodern schools of thought. As to the other dollar, the money's all there. They each paid $10. 3 times 10 is 30. $5 came out. There's 25 still in the drawer. Of the $5, 2 went in the clerk's pocket and the other 3 were distributed. The problem with this riddle has to do with language and method. When I say they each paid 10, they each got $1 back, so they each paid 9. What's 9 times 7? And you say 27. And I say, and the other 2. The language signals to you that you should be adding. 27 plus 2 is 29. However, that's a problematic method, for we are not trying to get to 30 anymore. We're trying to account for the $25 that's in the cash register. So 9 times 3 is 27. And what about the 2 in the guy's pocket? Well, you subtract those 2. 27 minus 2 is the $25 that was paid. All the money is accounted for. Sometimes the problem is with our method, and that's one of the driving questions in the philosophy of science. Is our method correct?